and we want to ask questions like, is there water on Mars? And of course, we have the Mars rover that landed late last year in about September, came back with the first spectra from rocks from Mars, and this is the way that we use to analyze the structure of rocks or to test for the presence of water on Mars. And we do it by looking at looking at the way in which the molecules within the rocks and the molecules of water absorb energy. And this is essentially spectroscopy. So last time we looked at how organic chemists, for example, separated mixtures by chromatography, distillation, and extraction, and so on and so forth. We had a brief look at purification techniques, so that you're essentially sort of geared up to do that sort of thing in the lab. But once you've separated compounds, then the question becomes, well, what are their structures? It's all very well to say that addition of HBr to an alkene gives you an alkyl halide. How do we know that? Well, you can take an alkene, you can mix it with HBr, and you can assume that you're going to get an alkyl halide. But in science, of course, we have to prove our hypothesis that we're going to get an alkyl halide by adding HBr to an alkene. So we have to provide proof of the structure. And all the rest of these lectures, sort of after the break for the next few weeks, are all going to be on techniques that we use to determine structure. And the first one is infrared spectroscopy. We're going to use photons in the infrared region of the spectrum that corresponds basically to heat. And we're going to absorb those photons, and the frequency, the energy of the photons the rate at which the photons are absorbed will be a function of the energy. So all spectra are plots essentially of energy. Here's the energy along the x-axis in the spectrum from Mars. It's marked wavelength, but a bit of level 1 physics tells you that wavelength is the same as energy, right? Wavelength is, lambda is related to frequency through the speed of light, and frequency is related to energy through Planck's constant, E equals h nu. So this is, albeit a little cryptic, this is an energy axis along the x-axis here, and you'll notice that at many different energies of infrared light, there is very little energy absorbed. We have a baseline along the bottom here, and then we have peaks. So at certain frequencies, energies, those photons are being absorbed by the rocks or by the water molecules on Mars. The photons are being absorbed, and essentially that translates to a peak along the y-axis. And every spectrum that we look at in this course is going to be a plot of energy versus either absorption or transmission along the y-axis. So spectroscopy is the there's many forms of spectroscopy at different energies. And in fact, in organic chemistry, to prove the structure of a compound, we find in practice that for most compounds, we actually need to do several different types of spectroscopy. Infrared spectroscopy that we'll talk about tonight, for example, is helpful in telling us about functional groups in molecules. So we've talked about functional groups, the ethers, the alcohols, etc., etc. And we talked about how there were two compounds in molecular formula C2H6O, dimethyl ether, versus ethanol. They have different functional groups. One's an ether, one's an alcohol. And in fact, infrared spectroscopy is very good at telling us whether we have an alcohol versus an ether, for reasons that we'll see tonight. However, infrared spectroscopy doesn't usually tell us the whole story. So it tells us a little bit about the functional groups. Next time, on Tuesday, we'll see how mass spectrometry tells us about the molecular weight of the compound, tells us a bit more information. And then, for the rest of the session, we'll focus on the most useful technique, nuclear magnetic resonance, or NMR. and we'll see how NMR gives us a lot of information as well. But in solving complicated structures, in practice, we need all of these different techniques. So once we have a pure compound, we need to know what's its structure. An example is pharmaceuticals, where if you want to patent a pharmaceutical, you have to prove the structure. You can patent the structure, but you can't patent an unknown compound that's got carbon and hydrogen and nitrogen in it, right? The patent office doesn't like that sort of thing, because everybody would be patenting their mystery compound that has carbon, hydrogen, nitrogen, and oxygen in it. So we need to prove the structure. Regulatory agencies require you to prove the structure. So structural characterization is important. Sometimes chemists have big arguments about structure. Here's a compound, hexacyclinol, where two chemists spent several years attacking each other in the literature about the structure. And Greffer had the structure at the top, which he thought was consistent with all the spectral data, whereas Rycznowski had the structure at the bottom, which I hope you can see. No matter how much little you know about structures, you can see that these two are really very different sorts of structures. There are many, many functional groups in this molecule. It's very hard to work out the structure. And even with all the advanced techniques that we have, including infrared spectroscopy, mass spectrometry, NMR spectroscopy for carbon and hydrogen, even then, it's not easy always to get a structure. So, at the end of this course, in the final exam, I will give you a bunch of spectra and ask you to determine the structure of the unknown. And you will find, just as I said, that it's not always easy. Okay. So, the goal here is to get you going on spectroscopy, right, and build your experience slowly. In the past, at McMaster many years ago, spectroscopy was taught all as one block at the very end of semester one, and then instructors would expect students to solve a structure in the final exam, and it didn't work well. Okay? So this is something where you need lots of practice. Okay? We'll learn this gradually so that you have an opportunity to practice a lot as we go. And in fact, I don't know, but in the second half of the course, 20B3 or 20, the equivalent 20D3 for the chemists, I have always continued to keep working on spectroscopy. It's a very sort of practical sort of thing. Many students like spectroscopy. They see this as a very real-world phenomenon, right? You are solving a real problem. And for those guys who don't like orbitals, where are they? Oh, there can't be many people like that. Okay? Then maybe this will be a little bit more appealing. Okay? The orbitals are extremely esoteric. This is very practical. Okay. So all of spectroscopy is the interaction of light, the electromagnetic spectrum with molecules. So it's the interaction of matter and light. Light can be thought of as waves. Oh, no, not waves again. Okay? Waves of energy or particles, packets of energy called photons. We're back to wave-particle duality. Let's not go down that road very far. Okay? And properties of light waves include wavelength and frequency and, in fact, energy. Wavelength, energy, frequency, as we've just said, are all really the same thing. And there are some equations for that from physics, right? So light, or photons, come in a huge range of wavelengths, a huge range of energies. You can see here that we start at the left-hand side with very high wavelength, or very high frequency photons, working to low frequency. The wavelength goes the other way, right? Nu equals c over lambda, I think, right? Where c is the speed of light, yeah? Okay, so that's from physics. So we have cosmic gamma rays, X-rays, very high energy photons, right, that we're familiar with, that will deliver a lot of energy to a sample of matter. Ultraviolet light, higher in energy than the visible region of the spectrum. Okay, and so that's why ultraviolet light can cause damage and skin cancer and things like that in a way that visible light does not, because we deliver more energy per packet, per quantum of light into molecules in the matter. Infrared lies on the other side of the visible region. So there's the visible region working its way from blue to red. So ultraviolet is to the left of violet. Infrared is to the right of red there. And we'll begin by focusing in the infrared region. Finally, we have microwave and radio frequencies, very, very low energy, very long wavelength waves of light that really behave mostly like waves and that have very long wavelengths. So typically, we're talking about wavelengths of meters, right? You tune your radio to 94.2 FM or whatever it is, right? And that is, in fact, the wavelength of photons that correspond to microwave radiation. And in fact, we'll see that in nuclear magnetic resonance, we're using that sort of frequency way down there in the radio frequency or RF region of the spectrum to excite molecules. And we'll get to that by next Thursday. Okay. This actually just really says that. I think I've already said that NMR spectroscopy involves radio waves. The information that we can obtain from NMR is specific arrangement of all carbon and hydrogen atoms in the compound. NMR is very good at telling us about carbon and hydrogen, lousy at telling us whether we have, for example, a chlorine or a bromine in the molecule. And we'll look at an example of that next week. So how do we deal with that? NMR tells us certain types of information with great precision, other types of information not at all. Infrared tells us about functional groups present in a compound, but tells us nothing about the chain length. Methanol's infrared spectrum looks somewhat similar to ethanol, to propanol, to butanol. It's the OH group that is the characteristic feature in the infrared spectrum. We can tell whether something's an alcohol from the IR, but we can't tell how long the carbon chain is. So you see, information is complementary. NMR tells us about carbon and hydrogen, but not particularly about the oxygen in an alcohol. It tells us how many carbons there are. It tells us whether we have, but or pent or prop, whatever, but it doesn't tell us about oxygen. Infrared tells us about the presence of the OH functional group, the alcohol, but not about the carbon atoms. UV-vis spectroscopy you'll meet in 20B3 uses visible and ultraviolet light, very important technique. Biologically speaking, UV-vis sort of area tells us about conjugated pi systems, bonds double bonds that are joined together. So a benzene ring that we saw, an aromatic functional group, 6-membered ring with 3 double bonds in it. That's a conjugated pi system. UV-vis, very good at picking that up. And those types of functionalities are present in nucleic acids. So, for example, we can quantitate nucleic acids with UV visible spectroscopy. We can also quantify proteins, because proteins also have benzene rings in their structure, phenylalanine, tyrosine, and the third one, whatever that is. Okay, so this chapter 15 focuses on infrared. What does all this say? Okay, right. So all of this sort of says that in this sort of spectroscopy, we are looking at the absorption of light by individual molecules. So when a molecule absorbs energy, okay, it can only absorb energy at certain frequencies. We saw that just before the break, right? If you excite the electrons in a carbon-carbon bond or a carbon-hydrogen bond, you can make them jump from the bonding molecular orbital to the anti-bonding one, but you can't make them hop somewhere in between. So they're quantized, right? We only have one type of transition that is possible for those electrons. And it requires absorption of exactly the right amount of energy. Now, in infrared, in the infrared area of the spectrum, we have less energy than that. UV visible excites electrons from bonding to antibonding orbitals, but infrared has lower energy, doesn't have enough energy to excite electrons from one orbital to another. But it can excite rotations and vibrations. And molecules can only rotate or vibrate at certain rates, at certain energies. So once again, these excitations of molecules to rotationally excited states, basically taking a molecule that's sitting still and suddenly making it spin, right? That's a rotationally excited state. And we can absorb a quantum of energy, a photon, and excite a molecule to a rotational state. But only certain rotational states are allowed, so only certain amounts of energy, certain frequencies of photons will be absorbed to excite a molecule rotationally. The same is true of vibrations, and it's mostly vibrations that we're going to talk about in infrared spectroscopy. These are vibrations of bonds. So we talked about how a bond sits at a defined length between the nuclei, but we can actually excite that bond and make it vibrate like a spring, right? So bonds are not just static things that sit there like rocks, solid. We can actually excite bonds, and we can excite them with even a small amount of energy into a vibrational state, like a spring. Essentially, we're going to take the bond, we're going to absorb a quantum of energy, and it's going to go boing, 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 like a spring. That absorbing of energy means that the photon is absorbed by the matter, and we can measure that absorption. And those vibrations will only be excited under appropriate quantized states. Okay. Each of the types of molecular motion describe how it is quantized. I think we've done that. Okay. So vibrational energies are separated by gaps. If a photon of light strikes the sample, okay, then with the exact right amount of energy, a molecular vibration occurs. Eventually, of course, this energy has to go somewhere, and it's released. The bond goes back, it stops vibrating, and that energy, of course, energy is conserved. Where does it go? It eventually corresponds to heating the sample. So infrared, right, we talk about sitting under an infrared lamp, it feels hot, right? So infrared light is being absorbed. It's not directly heating you. It's actually exciting vibrations in your bonds. Okay, and then those vibrations are stopping, and that energy is coming out as heat, so that if you stand under an infrared lamp, it feels hot. But the heating effect has come via the absorption of energy to create vibrationally excited states. Okay, so different molecules have different types of bonds, okay? And so not only will we just excite one bond, but at different frequencies, at different energies of light, we can excite a variety of different bonds. And so if we measure the absorption spectrum, if we measure what frequencies are absorbed by the sample, then we can translate that back and interpret it in terms of what sort of bonds are present. So what sort of bond vibrations can we have? The first one is fairly simple. It's a stretching vibration like a spring. So we've talked about that already. The bond sits at an equilibrium distance between the nuclei. We absorb light, and we go boing, 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 boing until we stop, right, like a spring. So that's a stretching vibration. The bond is stretched. There are also bends. So there are a variety of absorptions, such as happens for a methylene group, a carbon with two hydrogens attached. So some excitations in infrared are not just excitations of a bond alone, but it can be a whole functional group. And for a methylene group, okay, we have in-plane, we have in-plane bending, boing, 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 and then there's the twist that goes something like that, all right, and then there's a couple of stretching ones, and this is always the most fun part, right? So there's what's called the symmetric stretch of the two bonds. That's that one. All right. And then, at a different absorption of energy, different frequency, there's the asymmetric stretch. Okay, and that is that one. All right. We do that over here. It's so much fun, right? The symmetric stretch and the asymmetric stretch. So this gives you lots to do over the weekend in terms of working out all sorts of interesting and always appropriate, I'm sure, vibrations, stretches, and bends. Okay, so we're going to focus mostly on stretching because all this stuff with the methylene group is quite complex. There's several different absorptions. And it's really stretching that tells us about individual bonds. Yeah?
Is there something specific that makes a stretch as opposed to?
No, it's just that particular bonds will stretch at particular frequencies. And as it happens, and this is really almost fortuitous, it turns out that all the stretches are in one half of the infrared spectrum. And all the very confusing stuff, the in-plane bending, the scissoring, the asymmetric stretches, all this stuff, is all in the other half of the spectrum. So what that means is that that second half of the spectrum is almost uninterpretable. It's full of a whole bunch of different absorptions at different frequencies that are hard to interpret. And we call that part of the spectrum the fingerprint region. It's very unique to particular molecules. It's like a fingerprint. So that part of the spectrum is called the fingerprint region because each particular organic compound will have a different fingerprint. That's great if you've got a reference sample, right? If you have an authentic sample of benzoic acid and you want to know whether your unknown material is benzoic acid, compare the fingerprints. The problem is that it's more common that we are using spectroscopy to determine the structure of something nobody has ever made before. And in that case, the fingerprint region is essentially useless. So, we're going to have a rule in this course that says we never go in the fingerprint region. Okay? All right. So, stretching frequencies are unique to two atoms in a bond, and we can use those to detect particular compounds. And this is just a little bit of background on infrared light. So hotter objects emit more IR radiation, and we can use infrared imaging and so on and so forth. Okay? So the energy necessary to cause the vibration of a bond depends on the atoms in the bond. So a CH bond is different from a CO bond. And it turns out that CH bond, the amount of energy that we need to excite a CH bond into a stretching vibration is much higher than the energy that we need to excite a CO bond into a stretching vibration. So this means that in a spectrum, we will see if a spectrum of a compound that has both CH and CO bonds, we will see two separate peaks at two different frequencies. One corresponding to stretching the CH bond, one corresponding to stretching the CO bond. So, how does infrared spectroscopy work? An infrared spectrometer irradiates a sample with all the frequencies of light, and some of those frequencies are absorbed, okay, only when we can cause a vibrational excitation. All frequencies of light that cannot cause an excitation go straight through the sample. Frequencies of light that can cause an excitation are absorbed. And so we're going to plot the amount of light absorbed as a function of frequency of energy. Commonly, we put the sample on a neat sodium chloride plate. We use salt, NaCl, because there's very little absorption in the infrared region. There are no bonds, right? It's ionic. It's an ionic compound. Sometimes we can dissolve the compound in a solvent or use potassium bromide. Okay, so we take our sample and we put it into the infrared spectrometer and we're going to generate a spectrum. It's a plot, as we said, of energy along the x-axis. Here, our energy axis is different again. Remember that we said that energy and wavelength and frequency are all the same. In infrared spectroscopy, for historical reasons, what we actually plot along the x-axis is wave number. It's 1 over the wavelength in centimeters. Why? Because years and years and years of undergraduate students have been confused about the idea of wave number. Okay? So let's not worry about what wave number is. It's measured in centimeters to the -1. It's reciprocal centimeters. It's 1 over wavelength, right? So 1 over wavelength is related to frequency, and frequency is related to energy. So it's still an energy axis. Doing it this way basically gives me quite nice numbers, right? We don't have numbers multiplied by 10 to the power of 15 along the x-axis, and it's just convenient that way, right? So we have numbers that range from 400 centimeters to -1 to 4,000, but the key point here is that this is an energy axis. In infrared spectroscopy, and again, there's no real reason for this, it's just traditionally the way it's always been done, we measure the percent transmittance through the sample. This is essentially the opposite of absorbance. So 0% transmittance means no light of that particular wavelength comes through the sample, it's all absorbed. So 0% transmittance is 100% absorbance, and by standard but arbitrary for reasons, we put that at the bottom. 100% transmittance means all the light goes through, no light of that particular energy or frequency is absorbed. Okay, and so we're simply plotting the amount of light absorbed or transmitted as a function of wavelength. So remember that the vibrations are quantized. So here at 4,000 centimeters to the -1, we have photons that are not able to be absorbed by the sample because they cannot excite any particular vibration. They have the wrong energy. I forget, the left is too much energy or it's too little energy. Jesus, that's why wave numbers are so horrible. Nobody can work out which way the energy is going, but it's an energy axis, all right? I'll leave that to you. On the right-hand side at 400, we've now got the opposite situation. Too little energy or too much, no absorption. But as we trace this plot out, you see that at certain points, at 3,300 centimeters to the -1, light is being absorbed. Something is stretching. And I can tell you that, in fact, that type of peak, that very broad peak at 3,400 centimeters to the -1 like that, is, in fact, the result of the compound having OH bonds. It's oxygen-hydrogen bonds that are stretching. Remember that we said bonds to hydrogen, okay, require, was it more energy or less energy? I forget now. Than bonds between carbon and oxygen. So this is, in fact, what we would call an OH stretch. The fact that this peak is there means that this sample has OH bonds. What does that mean in terms of a functional group? It's an alcohol, right? If there was nothing there, if all the light at 3,000, right the way from 4,000 to 3,000 centimeters to the -1 passed through the sample, what could we deduce? There's no alcohol, right? So this is an on-off test. This is not quantitative. I can't actually tell whether this molecule has one OH group, or as in an alcohol, or two OH groups, as in a diol, or even three OH groups, as in a triol. Okay, it's not very quantitative, but we can tell that the molecule has OH groups. So there's at least one alcohol functionality in the molecule. All right, let's move along a bit. 3,000 centimeters to the -1. Several sharp absorptions there. And I can tell you that that is CH bonds. So this compound has CH bonds. Whoopity-doo, right? Every organic compound, almost every organic compound has CH bonds. So this is not particularly useful, but for the sake of argument, you could tell certain things about the compound that it has CH bonds. Over here, you see a whole lot of absorptions. Down here below about 1,500 centimeters to the -1, there's a whole lot of stuff. Difficult to interpret. This is the dreaded place where we are not allowed to go in this course. It's the fingerprint region, right? That's the fingerprint. So, if this is an alcohol, if this is pentanol, hexanol actually would have a slightly different fingerprint. But if I had authentic samples of pentanol and hexanol, I could tell which one I had by looking at the fingerprint. But it's not enough to be able to tell without those standards. Fingerprint is too complicated to tell which alcohol I've got. Yeah. Okay, so we would call these peaks. It's sort of Bose-Ackwards, okay? I admit it, right? It's because this is transmittance. You could, if you wanted to, turn the whole thing upside down, right? It would be a perfectly good spectrum. It's just that for some reason, and it's mainly historical, chemists always do it this way. In NMR spectroscopy, you'll find the peaks going the right way. They're going up. Okay? It is arbitrary. Yeah? So in this case, it's the troughs that you're looking at, right? Yeah? I know it's a bit confusing, but every infrared spectrum ever run by man, and back in the days before NMR, infrared was one of the most sophisticated techniques chemists had. And you can see that it's quite limited. It tells us something about the structure of an unknown compound if we record its spectrum. But it sure as heck doesn't tell us everything. All right, any questions about the spectrum? Let's move on. That just tells you how to calculate wave number. That's physics. Equation will not be on the test, okay? C is the speed of light. Anybody care? No? Same spectrum, same wave number. Mystery axis along the x-axis. And that asks you the same thing. So the signal in the infrared has three important characteristics: wave number, intensity, and shape. So the one at 3400, we would say was an intense absorption, right? The percent transmittance drops almost to 0. Notice that there's a couple of little humps. There's a little hump there around about 1700 centimeters to the -1. Okay? One of the mistakes that lots of students make is that you want to interpret those tiny little things. They're tiny. They're not important. They're not telling you anything about the structure. Okay? So real-life spectra have these extra little blips in. In fact, that signal right there, I believe, is you get signals from carbon dioxide in the atmosphere, right? It stretches as well. So carbon dioxide, water, traces of impurities may give you little glitches. So we're looking at the big picture here, the OH group, the CH group. So this is a compound that has OH bonds and CH bonds. And that's about all we can tell. So we're looking at the signals that are intense, and the final thing is shape. Notice that the OH bond is a broad absorption, okay? But the CH bonds are much sharper. And the broadness of the OH bonds comes about because the hydroxyl groups are hydrogen bonding to one another in the sample. So in fact, there's a whole range of different OH bonds stretching at slightly different frequencies depending on how strongly each individual proton in each individual alcohol is hydrogen bonded. So that gives rise to the broadness of that shape. Do CH bonds hydrogen bond? No, right? No dipole in the CH bond, not polar. So CH bond stretches by comparison to the OH much sharper. So there is quite a bit of information in the infrared. Why do things stretch at different frequencies? And you can do some math for that. Anybody care? Nu bar is 1/2 Pi. Pi because all mathematicians always put pi in a formula. It looks better that way. Okay. C is the speed of light. Any formula written by a mathematician that didn't have a C in there would be far too simple, right? Okay. F. That's about all you can say about this equation. Oh, F, this equation, right? F is the force constant. So what that really is saying, it's the F bit that's important here, right? So different atoms held together in different bonds. Different bonds have different sort of stretchability, like different strength springs. And that's the force constant influencing the frequency, and that is why CH bonds stretch at different frequencies than OH than CC. The reduced mass is at the bottom, M1, M2 over M1 plus M2. All you need to know is that hydrogen is light. Carbon, oxygen, nitrogen, all those other atoms in organic compounds are heavy. So if M1 is carbon at 12 and M2 is hydrogen at 1, M1, M2 is 12 over 12 plus 1 is 13, close to 1, right? Let's do the same thing for a carbon-carbon bond. 12 times 12, 144, divided by 12 plus 12, 24 is 6, 5, 6-ish, right? It's a bigger number than the CH bond number, right? So that just tells you why it is that all the bonds between carbon and hydrogen, oxygen, hydrogen, nitrogen, hydrogen, all the bonds to hydrogen are on the left-hand side of the infrared spectrum. Notice that in this previous spectrum, right? The CH and the OH bonds were all here, 3,000 centimeters and above. So bonds between a heavy atom and hydrogen are on the far left. Heavy atom stretches all the way down to about 1,600, second part of the spectrum, and below 1,600 is the dreaded fingerprint region where we're not allowed to go. Okay, got it. So, bonds to hydrogen. Notice that M1, M2 formula, that reduced mass formula, tells you that the OH bond here is actually absorbing at a different frequency than the CH bond because oxygen and hydrogen have different weights.
Yeah. Wouldn't you see the CC bond, the carbon-carbon bond on the thing? It's a heavy in the middle?
We'll get to CC bonds in a minute. So, okay, so we've been through all that, and there's some bond stretches, CH, CD. Notice the heavy isotope of hydrogen, deuterium, changes the frequency of that stretch a lot, right? Go from 3,000 to 2,200 centimeters to the -1. Here's the carbon-oxygen bond. It's about 1,100 centimeters to the -1. So can we detect whether there's a CO bond present in the molecule? The answer is no, because 1,100 is into the fingerprint region. So if you look at an infrared spectrum and you see something at 1,100 centimeters to the -1, the one big mistake is to say, oh, I'll look that up on the chart. 1,100 must be a CO bond. And the problem is that down in the fingerprint region, there are all these other things going on. And so you can make a mistake. And that's the problem with the fingerprint region. Okay, you can misinterpret absorptions in the fingerprint region, and that's why it's a good idea not to go there. So, CCl. Alkyl halides, actually difficult to detect by infrared. Notice chlorine, very heavy. So now our reduced mass drives the CCl to 700 centimeters to the -1. The force constant, however, is important. Double bonds are stronger, stiffer springs than single bonds, and triple bonds even more so. Here is a cyano group in a nitrile, 2,200 centimeters to the -1. So now we're out of the fingerprint region for a C triple bond N. We can detect whether the compound has a cyano or nitrile functional group. C double bond N, as in an imine, 1,600 centimeters to the -1. There we're all right. So CN double and triple bonds, and in fact CO double bonds is the most useful one, are okay. But we can't tell whether something has as an amine as with a CN single bond, because now that frequency is down to 1100, we're into the fingerprint region, and we might make a mistake in interpreting an absorption at 1100. Okay, so infrared tells us about certain types of functional groups. So we can make a chart of where things absorb. XH, triple bond, C triple bond C, C triple bond N, 2100 to 2300, CC, CN, CO, 1600 to 1850. Okay, and this type of information in some form or another will be given to you on tests. Okay, so you'll be given a chart of infrared absorption frequencies that might look something like that. Yeah.
Sorry, what's the CZ bond?
That's deuterium, the heavy isotope of hydrogen, right? So deuterium weighs 2, right? So you do the M1, M2 over M1 plus M2 calculation and replace H, do it for H at 1 and D at 2, and you find you get a different number, right? Okay, so what we cannot determine, because they're all down in the fingerprint region, is the presence of single bonds. Does that make sense? Okay, so we can't do single bonds, but we can do double, triple, and bonds to hydrogen. So there's the fingerprint region, and the rest of it is called the diagnostic region because we can actually use it to make a diagnosis of our structure. Okay, so here now is 2-butanol. The diagnostic region, this is the same spectrum, we've talked about it. The diagnostic region shows you the OH stretch here, the CH stretch here. Where's the CO single bond stretch? It's down there in the fingerprint region somewhere. We're supposed to have one at around about 1100, right? And there's a whole load of peaks at 1100, and there's the problem, right? You really would, if you had this as an unknown compound, you really would be risking it to go in there and say that peak at around about 1100, that's got to be a CO stretch, right? Okay, so that's that one. The rest of the slides. Okay, so there's isopropanol for comparison. 2-butanol, isopropanol. You see, they are different, and if you look at those two slides, I can't put them both up at the same time, but if you look at them carefully, you'll see that the fingerprint regions are really quite different there. Yeah? The problem is that we can't make a diagnosis from the fingerprint region. Okay, so we've still got the OH stretch, we've still got the CH stretch. They're there in both compounds, so the diagnostic region doesn't distinguish between isopropanol and 2-butanol very well. Right? So the key point to understand here is that we're learning something about molecular structure. Not everything by any means. We're going to need other techniques to solve structural problems. Oh, there we go. We've compared them. Oh no, there's the force constant thing again. CH or OH bond is stronger. Hybridization. We haven't talked quite about hybridization yet in chapter 1. But it turns out that CH bonds, even though they're all single bonds, carbon-hydrogen bonds in an alkane are actually slightly different frequency than an alkene, slightly different frequency than a compound with a carbon-carbon triple bond in it, an alkyne or acetylene. So depending on the bonding of the carbon, the CH stretch is different. So this gives us quite a nice way to determine a little bit about structure. Right? Let's say that I have an unknown compound, all right, and I look at the CH stretching region. Let's go back to isopropanol just for a minute. Where was that? Okay, and so here's my CH stretching region, and you see all those CH bonds are at or below 3,000 centimeters to the minus 1. So those are all on, so that tells us that there's no alkene in this molecule, right? This is a saturated alcohol. What else can we do here? Oh, there we go. There's a typical sort of representation of an alkane. You see nothing below Nothing above 3,000, an alkene, and an alkyne with a CH bond in it. Quite distinguishable characteristics. Okay. So, of course, we have to be careful. Here is an alkene and an alkyne that don't have CH bonds on those carbons. So, when we're looking in the diagnostics, we can't prove in infrared that we don't have an alkene, but it would have to be a tetrasubstituted one with 4 bonds to carbon or oxygen or nitrogen and no bonds to hydrogen. Okay, ketones, very good. Resonance, we'll talk about. But this is actually one of the strongest peaks in an infrared spectrum, the presence of this carbonyl group that is present in ketones and esters, carboxylic acids, amides, a whole variety of different functional groups. So, and again, we see a very strong absorption right around about 1720 in a ketone. And if we want to get subtle about it, you can see that that frequency changes a little bit as the CO double bond is present in a ketone versus an ester, whether that compound has a CC double bond attached to the carbonyl. So carbonyl group, the presence or absence of the carbonyl group is one of the key characteristic things that we can establish with infrared spectroscopy. Very strong absorbance, right around about 1,700 centimeters. And if you want to get picky, you can actually tell even more about what is attached to that CO double bond. Okay, so the strength can vary. Strength is a function of the dipole of the bond. So it turns out that a very symmetric bond with no dipole, like a CC double bond in ethene, for example, there's no dipole and it's a symmetric molecule. And in fact, absorption turns out to be very weak in those cases. So the absorption of light, the physics of the mechanism of the absorption of the photon, is actually a function of interaction with the electromagnetic field of the photon interacts with the dipole field of the functional group. So CO double bonds, always very strong, very good diagnostic, because there is always a dipole in a CO double bond. Alkenes, alkynes, we have to be much more careful with, because if they are highly symmetric, then the signals can be very weak. That slide I will skip over. Those who care about the physics can see that there's an equation there that tells you about dipoles interacting with partial charges. Okay, and that says the same thing. So here is a typical carbonyl group. Okay, very strong absorption at 1720 centimeters to the -1. Notice it's much stronger than the stretch of a carbon-carbon double bond because now there is very little dipole in the alkene CC double bond. So we can always tell whether there is a carbonyl group present in an organic compound from infrared. So what have we learned? We can tell whether there are carbonyl groups present. We can tell whether there are CN triple bonds present. We can tell whether there are CH bonds present and whether they are on alkanes, alkenes, or alkynes. Right? We can see whether there are OH bonds present. NH bonds in amines can also be detected. So in combination, infrared is quite useful. It tells us quite a bit about the structure of an unknown molecule. But is it enough to solve everything? And the answer almost invariably is no. Oh, okay, so the intoxilyzer that tests for blood alcohol uses infrared, for those who can. Broad and narrow signals, we kind of covered this. So broad signals, OH stretching signals, are often quite broad because those hydroxy groups, like water, can hydrogen bond to one another. Narrow signals when they don't. And there's a picture of the hydrogen bonding. Okay, and you can see that as we draw that hydrogen bond there, we alter the strength of the existing OH covalent bond. So we have a whole range of molecules with different strength OH bonds, all absorbing at slightly different frequencies. And that gives rise to a broad signal. Okay, so this can actually tell us about concentration, for those who care. OH participating in hydrogen bonding, you see there it's broad. At some concentrations, the molecules don't form OH hydrogen bonds, and we get sharp signals and so on and so forth. Carboxylic acid has an OH bond, very, very broad signal. But notice that we have another diagnostic for a carboxylic acid. So an alcohol has an OH bond, but no CO. A ketone has a CO double bond, but no OH. A carboxylic acid has both. And so here is a typical sort of infrared spectrum of a carboxylic acid. This very broad OH due to hydrogen bonding, and the CO double bond right there at about 1700. So we have a way to distinguish between carboxylic acids, ketones, and alcohols using infrared spectroscopy. Okay, so hydrogen bonding in the carboxylic acid. For the molecule below, predict all of the stretching signals in the diagnostic region. Is this the last one? No. Oh, shit. Okay, all right. Okay, so I'll leave you that as an exercise to do. Amines. I think I mentioned this, right? So really these slides are here so that you can just see a few examples of what infrared spectra look like, right? Remember that amines, like alcohols, we have bonds to a heavy atom, right? So CH bonds below 3,000, NH above 3,000. Primary amines, we see two peaks. Secondary amines, with only one NH, we only see one peak above 3,000. So once again here, you know, we are not going to convert you instantly into experts at interpreting infrared spectra, right? The key point to take home, however, is that there is quite a bit of information in these spectra that tell us about molecular structure. Oh, the asymmetric and the symmetric stretching. Yes, so the NH2 group, right? There's two peaks because that pair of NH bonds can go symmetrically, asymmetrically, or symmetrically. Right, get it? Yeah, we've been there, we've done that. So here is just a specific example showing you that. Whoa. How to solve a problem. Okay, table 15.2 summarizes some of the key signals that help us to identify functional groups present in molecules, and you will be given this table in all exams. So, there are some examples on the first assignment which will be coming out. We will probably be posting that certainly by Tuesday. I know it's supposed to only go up Thursday. But there are a bunch of examples that just give you very simple infrared exercises. Here's a spectrum. Is it butanol or butanal, right? The aldehyde. Is it butanoic acid or whatever? And just work your way through those. Here are just some key things that you can do to help you, as you look at those infrared spectra, decide what regions to look at, okay? And ask yourself whether there are troughs there, and away you go. This one has no NH bonds, no OH, no carbon-carbon triple bonds, and so on and so forth. So this is a typical alkane. So IR analysis, here's a reaction. Okay, we've seen that you can convert an alcohol to a ketone, lose hydrogen here. Earlier on, we saw that loss of hydrogen is an oxidation, right? So this is an oxidation reaction. I take my cyclohexanol, and I'm going to react it with an oxidizing agent, and I should get cyclohexanone. So, how might IR spectroscopy be used to analyze the reaction? So I do the reaction, but I don't know that it's worked. So I isolate the product. It might be cyclohexanol again, Or I might have got what I wanted. I might get cyclohexanol. How are these different in the infrared? Right? C double bond O, carbonyl group, always strong, right, at about 1,600 centimeters, so 1,700 centimeters to the -1. So if I made the ketone, I should see that. If I still have the alcohol, no C double bond O, but I should have OH stretch at about 3,300, right? But no CO. What if I had a mixture of the two? You're going to see both, right? Yeah? So you have an analytical technique that is now beginning to tell you about whether a reaction worked. Let's say that you have a mixture. You have a mixture of the alcohol and the ketone. What do you do next in the lab? Got to separate them, right? How do we separate things best? Chromatography, right? So here's an example, right? You do the reaction, it's 90% done, but you've stopped it. So now you have to go in and separate using column chromatography. You do column chromatography, you've got two fractions. One's the alcohol, one's the ketone. How do you know which one's which? Run the infrared, right? Yeah? All right. Very good. So I think we're just about there. I don't think there's anything else tremendously important here. Oh, what can we deduce? Right. So I will leave you that as an exercise, given the time. Okay. And so have a look at that spectrum. See what you can deduce. Away you go. Which compound led to this spectrum? Is it A or B? And you should now be able to do those sorts of exercises.